Okay, going on to part 2 actually. Of chapter 2, dealing with equations. We're going to look at the addition and multiplication property of equality. Now in our textbook they show us sort of a scale in which the items balance. And this fulcrum can be thought of as an equal side. So this side equals the weight of this side. Now, if we add something to this side, it's not going to be balanced anymore. But if we add something to this side, the same amount, we will continue to balance that. Now, it's not the same amount anymore, but it's still an equality. That is, it still balances. So as we look at example 1, and by the way, this is an expression. This is an expression. Now, when we add an equal sign in the expressions, or one side to the other, this makes it an equation. So the difference between an expression and an equation is that the equation has an equal sign, and then you're asked to solve the equation. And these steps that we add something to both sides to keep the balance, we multiply each side by something to keep the balance. Those steps are called solving the equation, which is a crucial part of your understanding of algebra. Now, as we look at this equation, our purpose is to isolate the x. So on one side we have the unknown, all by itself, 1x. And then on the other side we have a number. Then x equals that number. We have solved what that unknown is. Now, as you probably imagine, we're going to start off real easy. And you might look at that first equation. And what would we do to isolate the x? Well, we have a -7. We want to make that a 0. What do we add to a -7? Well, if you recall, it's additive inverse, which is a +7. But in order to keep the balance, we must add the +7 to the other side. And now we do our addition. And this side then, we're left with just the x, and this side, the answer, or the solution. We've isolated the x equals 17. This simple step we did, and later there are going to be many steps involved, this is solving the equation by adding something to both sides to keep the balance until we isolate our variable, 1x. Going on to example 2, again a very simple equation. A letter, a number, a number. We want to isolate the letter. So we're going to add the additive inverse of a positive 0.6 with a negative 0.6. Put that to both sides. We then get a y by itself, which is what we're looking for. And then this becomes a negative 1.6. This simple step here is referred to as solving the equation. Now, as we go on to example 3, you see it's starting to get a little more complex, but we're going to bring in stuff from section 1 of chapter 2. And as you look at this, you're going to collect like terms. So this is our next step. Collect like terms. So this is going to be a 5x, and this is going to be a positive 2. This is going to be a 4x and a negative 1. So we've made what seems like a little complicated equation into something more simple because we've collected like terms. And this is often where you want to be for this next step, which is to get all of the x's on one side. And you want to try to keep your x's positive. I'll get into that later. But what we want to do then is the additive inverse of a positive 4x will be a negative 4x. This then gives us x plus 2 equals a negative 1. And now you'll notice we are like we were in some of the other examples. So to isolate the x now, we want to do the additive inverse of a positive 2, which is a negative 2 to both sides. Then add them up, and we get x then equals a negative 3. Now, so far we haven't checked any of these by putting our negative 3 into the system to see if in fact it works. And by doing your practice and then later the quiz me, that is your check. But there are sometimes examples given where that's all they want you to do. Is this a solution for this equation? Going on to example 4, we see we have parentheses. And in my original, I forgot to put a negative there, so I'm doing this again. Distribute the negative 5. That gives me a negative 10a and a positive 5. Now, when you have a negative sign in front of parentheses, all you need to do is to remove the parentheses and change each of the signs. So this was originally negative, now it's positive. This was positive, now it's negative. So we then go on to our next step where we collect like terms. These two end up with just an A. And we have a negative 6 and a positive 5. Leave me with a negative 1, and that all equals 7. So we've got to a place where we have an A all by itself. How do I get rid of that negative 1? By adding its additive inverse, and again, to both sides. So we have then A equals 8. And if you put that in the original equation, this does in fact check. When I usually do these, I put up over here on the right of the board the steps needed to solve the equation. Now what we've been doing is building up. So in some of them they were very, very easy. But then we went on to number 2, get rid of grouping symbols, which is usually a parenthesis. Then we combined like terms. Then we were to isolate the x so that you have a 1x or whatever variable you have. And we did this through a process that we'll describe a little later called transposition. But right now we've been using the additive inverse. And you've seen that illustrated. But now we're getting to something that usually you do first, but we didn't have any examples of it yet. And that is to get rid of fractions. So as we see in example 5 now, we have a fraction. And this is the simplest type, in which you have a fraction next to the letter x, the variable, and just a term on the other side. Now here we're going to pull into our repertoire of things. How do we get 5/2 to be a 1? And you think back just a little bit, the multiplicative inverse, that is the reciprocal of that number. If we multiply this number by its reciprocal, and we have to do that to the other side too, notice what happens. Here, all of this cancels out, and it just becomes a 1x, which is what we're looking for. Remember, this is over 1 too, so we can cancel a 5. And then we end up with our x all by itself. And our denominator is going to be 1 times 1 is 1. So 3 times 2 is 6. Now, here's a case that if we wanted to check it, we could easily do that. Put the 6 where the x is. 2 goes into 6 3 times. 5 times 3 is 15. So again, this checks. So in some cases, we're going to use the multiplicative inverse. These are techniques that we're going to use to isolate the x. And there are more. But right now we're doing it slowly. Again, keeping this in mind, whatever we do to one side, we do to every term on the other side, so that we keep the whole thing balanced. It's not the same equation, but it's an equivalent equation. And we're looking to get x by itself equals a number. That is the solution. All right, going along to example 6, and we're on page actually 89 now. And we're starting off easy. We don't want to get to the real difficult ones yet, but the pattern is what we're looking for. Now here we have a negative 3x equals 33. And again, we don't have fractions, we don't have grouping symbols, we don't have to combine like terms. We're actually at step 4 where we want to isolate the x so that it's a 1x. Additive inverse is not going to work out. What we are going to use is this new step here where we call divide by the numerical coefficient of x. Now we had some lesson on this earlier. What is the numerical coefficient of this number? Well, it's a negative 3. So if we divide this term by a negative 3, and this side by a negative 3, we have kept the balance, but now the negative 3's cancel out. And we have x then equals a negative 11. Now this is a technique we're often going to use. We're going to be dividing something by the numerical coefficient of x. whatever that is, once we've isolated the x term, that's a good method. And we get our solution. Oh, and one other thing. One of the reasons we tried to keep our x's positive, I had said I would mention this, is that if you have a negative x that you're dividing by, sometimes students, when they get to this side, they'll divide by 3, but forget it's a negative. So if you don't have that, you don't have to worry about that. So that's a little hint they give us in our textbook too. Try to keep your x's positive because we want to have what a positive x is. In example 7, again, a little twist of what we've had. So this is a fraction. Now, keep in mind there is a 1 here. So in a sense, our fraction is 1/7. Well, if we want to get y by itself, what are we going to multiply by? Well, the multiplicative inverse, which is 7/1. Now, we can write this just as the 7. So let's change color here a little bit and say we're going to multiply both sides by 7. Well, that green is not too dark, so let's try black here. That's better. So again, we're multiplying this by 7/1, but we don't have to write the 1. And here the 7's now cancel out. And we get on this side our y all by itself. And this is 140. So again, we're using a variety of techniques here to isolate the y. Okay, going on now to example 8. I worked a little bit of it out. First thing you want to do is no grouping symbols, combine like terms. So this becomes a 4a, the 2a by itself. This adds up to a -20, and a +10 gives me a -10. So we're going to start to isolate the variable in this case, trying to keep it positive. So we'll subtract its additive inverse from both sides, and we end up with this. Now here's the case where we get 2a by itself equals something. So here we're going to divide by the numerical coefficient of a, which is 2. This is often the case. And the 2's cancel out, and we're left with an a by itself equals a -5. So once again, they're getting a little more complex. Notice one of the things I've also done is try to keep the equal signs lined up. In the concept of this balance, where we do slight things to each side until eventually we get to this. This then is the solution. Okay, as we go on to example 9, we're going to deal with some word problems. And we did a little bit of this earlier. And here it says the sum of two numbers is 8. One number is 3. How do you put that into an equation to find what the other number is? Well, x's are unknown. We know that the unknown plus 3 is going to equal 8. And I'm going to introduce a new term here. It's on our list. It's called transposition. When you take a number from one side of the equation and bring it over to the other side. As it crosses the equal sign, the sign of the number changes. So on this side it was a positive 3, on this side it becomes a negative 3. And it's sort of like adding a negative 3 here, adding a negative 3 here. It's just a shortcut. And then you have 8 minus 3 is 5. Now a picture of this would be if this is x, or I guess I have this the other way. If this is 3 and this is x, what will x be to give you the grand total of 8? Well, here we can figure out visually that x will be 5. But here we solved it algebraically. Now another one they want you to keep in mind is the sum of two numbers is 8. If one number is x, what is the other number in terms of x? So here if we look at our picture, it helps us a little bit. The total is 8. One number is x. So what would the other number be? Well, it's going to be the whole of 8 minus the x. So that is our answer for that part. Now for some of these, if you're like the average student, as you read a word problem in English and you have to convert it to algebra, you're going to need to read it again. And in some cases, you're going to look at the tutorial bars over on the right of your screen, show me how to do this, read the textbook a little bit more to get some of this information. We're looking for conceptual things here. Here we have an 8-foot board that's going to be cut into 2 pieces. So there's my 8-foot board that I'm going to cut into 2 pieces. And if one piece is x, what would be the length of this other piece? Well, deja vu, what we just did, can you see it's going to be 8 minus x? By the way, if you added these two together, the x's cancel out and you end up with 8. But this is an excellent technique for if you have something and you want to divide it into 2 unknown parts. This is a part that's unknown and this is a part that's unknown. But you are giving it some algebraic symbols to represent those parts. In example 10, and we are on now page 91, and again, you want to read the text, especially if something's unfamiliar to you or you see it here and you still don't get it. This is just an outline of what we're doing. But we're going to talk a little bit about what we call consecutive integers. Give you a little background on that. Now, let's say we start with 5, 6, and 7. Now, these are 3 consecutive integers. But we want to put them into algebra, so to speak. So our first integer will be x. How do we write 6 now in terms of x? Yeah, x plus 1. And how do we write 7 in terms of x? X plus 2. So if x is 5, then we have 6 and we have 7. So we have written 3 consecutive integers. Now we can change this to 8, 9, 10, or 100, 101, 102. This pattern would still be the same. Now, what would be the sum of these 3 consecutive integers? Because that's what they're asking us here. Well, we just put a plus here, and we have, collecting like terms, 3x plus 3. And by the way, the sum of 3 consecutive integers is always 3x plus 3. Now, let's do something a little different beyond this example here. Suppose we had odd integers. Now, our first odd integer, let's say, is 7. The next one is 9. And the next one would be 11. So how do I write 7 in terms of x? Well, that's going to be x. How about 9? Well, that would be x plus 2. How about 11? X plus 4. Now, when students see this and they're asked for odd integers, this is sort of an enigma for them, a mystery. How could you add 2? 2 is even. But the key to all of this is defining your first integer. If your first integer is odd, then to get to the next odd integer, we have to add 2. And of course, the 4 for the next one after that. Now, an interesting thing happens. If your first integer is 10, how do I write 12? Well, interestingly, it's exactly the same way. You're going to add 2 to it. And then to get 14, you add 2 to that. So this is what really blows some students' minds, is how can this be the same for both odd and even integers? And again, once again, the key is, what integer do you define first? If you define an odd, then by adding 2 you get the next odd. If you define an even, by adding 2 you get the next even. So a little bit of background on consecutive integers. And later we'll be dealing with some problems